Hello everyone. In last lecture I was discussing about weld fatigue life assessment procedures. There I have already discussed about nominal stress method. Today I will discuss about more details on nominal stress method, and I will solve some problem on nominal stress method for welded structure. So, this is the content of today's lecture. That means first of all I will discuss about what it called detail fatigue class, then I will discuss about Eurocode details class, then I will solve some problem on what it is called problem on nominal stress approach, and finally I will discuss about concept of notch stress, which will be required for another fatigue life assessment method, that is called hot spot stress method. So, first of all we should know what is fatigue strength, or it is also called FAT. This you should keep it in mind. So, fatigue strength based on IIW means International Institute of Welding. The fatigue strength generally is given at 2 into 10 to the power 6 cycles. Generally at this cycle level for a particular structure, whatever the stress value you can get, that is generally known as sigma f, or this is also called FAT value, or this is also called fatigue strength of that structure. Okay. For a particular types of what is called geometry, this FAT value is different. For different types of weld geometry, this FAT value also will be different. Generally this FAT value is plotted in a SN curve, where generally the slope is 3 before 10 to the power 7 cycle, and the slope is 5 after 10 to the power 7 cycle. What does it mean? That means once we draw the fatigue curve in SN stress versus strain diagram, then what happens, the fatigue curves is look like this. Initially the slope is 3, after that generally this slope is little bit increase. Okay. So, here you can say this slope is 3 and here slope is 5. So, this is 3 and this is 5, this you should keep it in mind. So, this the value of number of cycle from where the slope is changing, that is your 10 to the power 7 cycle, and this FAT value generally is calculated, or you can say is determined based on a what it is called survival probability 97.7%. So, this is survival probability. If this is survival probability, then what will be the failure probability? So, you can say opposite way, that is failure probability will be equal to 100% minus 97.7%, that means 2.3%. That way you can write what I am telling, understand. So, failure probability is 2.3%, whereas survival probability is 97.7%. This generally SN curve is plotted. And another things you should keep it in mind, this FAT strength generally calculated for a stress ratio. You can say what is a stress ratio R? R you know, that is means your sigma mean by sigma max. This is generally considered as 0.5, and which is at a high mean stress. This you should keep it in mind. This fatigue strength is calculated for FAT class generally for a R value of 0.5 and at a high mean stress. This you should keep it in mind. Why high mean stress? Because it is assumed in case of welded structure, generally we know that in welded structure at weld zone for steel types of structure like mild steel, in weld zone it is tensile types of residual stress created. This magnitude of residual stress is quite high, that is within a range of yield strength, you can say, of that material. That is why this assumption generally also included during FAT experiment to determine this FAT value, That is why they consider here a high mean stress with an assumption of high tensile residual stress in the weld. That is why what happens, this high mean stress they have considered. Now, I am going to show you how this what it is called fat strength according to IIW for different types of weld geometry, that you can see from here. So, here you can see this curve generally represented the fat strength for different types of configuration of welded joint. For a fat value of 40, how the curve is look like 40, 50 you can see, then 63, 80, 100, 125 and maximum it is limited up to 160, that you can see. So, here one things you can observe, initially what happens, what I have already shown, that initially up to 10 to the power 7 cycle, here the slope generally is the slope k equal to 3 for for 40 to 125 fat value, but you always keep it in mind, on the fat value is 160, there the slope k is started from, you can see slope k is started from k equal to 5 itself, this you should keep it in mind. For rest of the cases, generally initially what it is called like 125 fat value onwards up to 40 fat value, the slope initially k equal to 3 up to 10 to the power 7 cycle. After 10 to the power 7 cycle, this value is generally changed to k equal to 5, k become 5. Okay. Now, here generally for different types of weld geometry, what is this fat value, that I am just showing, because this fat value is a very important parameter for calculating fatigue life based on nominal stress approach, because I have already shown you what are the steps generally followed in case of nominal stress approach. That means, first of all we need to decide what is the fat value according to the geometry of the weld structure. Then what happens, that things we can get from this classification society, as well as this different types of standard are they are like here one of the standard I am showing, that is IIW standard. So, here one things you can observe, for these types of weld configuration where generally a weld is extra specimen which is generally put it welded like this, if it has a structure like this and if it is subjected to a parallel types of loading, here you can see, then this fat value we need to consider for these types of geometry within a value of range of 40 to 50. If the you say a gasket is put over a flat plate and you can see the welding is done around this gasket and the load is acting you can say parallel to this gasket. In this case you can observe this fat value can varying from 50 to 80. Then for cruciform types of weld joint generally it is you can see it is considered here 63. For these types of another weld joint it is 71. For single fillet weld and its load is transverse in nature, that is called transverse plate. So, here it is value is 80. So, what happens for butt weld you can see, and this transversely this load is acting. What is transverse butt, what is parallel butt, little bit I am just telling, then it will be very clear to you. Generally once the this is a butt welded plate or butt welded joint you can say, where butt welding is done like this. So, if the load is acting parallel to this weld line, let us P, then it is called parallel butt weld. If the load is acting, let us that this is the butt weld. If the load is acting perpendicular to the weld line, then this is called transverse butt. Transverse butt joint, that you can say. So, generally this transverse parallel this thing is coming depending upon the loading direction, that you can say in a welded structure. So, this is a parallel butt, this is a transverse butt joint. So, this is a transverse fillet, you see this 80 case is transverse fillet. So, different types of configuration, generally what happen, this fat value is different, that thing generally how it is plotted, these things plotted generally number of cycle versus the you can say stress range, y axis is a stress range, there generally it is plotted. So, here this data generally is gathered based on experimental observation. After that generally for different types of geometry, generally this SN curve is plotted. This SN curve generally according to the recommendation of IIW are characterized the generally fatigue strength at 2 million cycle. So, this at 2 million cycle whatever the fatigue strength we used to get, that is generally called fat class value. This you should keep it in mind, that is called fat class value, its unit is generally Newton per millimeter square or you can say megapascal. And this curve for welded joint generally are limited by, you can see for a fat value up to 160, which I have already told you. For this case generally the parent material which is used here is steel material, and in this case you can see the only in this case you can say the this fat curve is started with a k value equal to 5, this you should keep it. In other case it is started generally for a k value equal to 3, okay, and after 10 to the power 7 cycle it become 5, this you should keep it in mind. Now, here another things you should keep it in mind, this fat class whatever the SN curve we observe, generally during experiment time whatever the misalignment of a joint is there, that thing generally incorporated in this that effect, that misalignment effect generally incorporated in this what is called SN curve fat data, this you should keep it in, that things I have written. Typical misalignment effect are already included in the fatigue classes, whatever the fat data is there, here typical misalignment effect is already considered, and these were present in the underlying fatigue test. This is actually IIW standard, similar types of other standard also available for this fat data, that I am going to show, like another standard I am showing for your just information, you can say. For Eurocode 3 generally detailed classes of you can say fat detailed fat classes is grouped into 14 main classes. So, this 14 main classes is tabulated here, you can see this is actually this fat value or fatigue strength value for a load cycle, you can say for a load cycle of 2 into 10 to the power 6 for different fat standard, generally which can be represented as NF equal to D divided by range of stress to the power m, this you should keep it in mind. For different types of fat class, let us fat 160 class, that means fat 160 class means whose fatigue strength value is 160 MPa, that a number of cycle is 2 into 10 to the power 6, this you should keep it in mind. Now, if this types of a structure, that means for a particular what is called welded structure where the fat value is 160, for that types of structure if it is subjected to some other range of stress, delta del sigma r, same structure if it is subjected to, then what should be is fatigue strength value, that we can easily calculate. Let us for a particular welded geometry, what does this equation means, that you need to know. Let us say this is for a particular welded geometry, that is transverse butt weld. Let us consider the fat value is 100, fat value is 100 MPa. So, this 100 MPa, this fatigue strength we can get when this equation, that means whatever the equation number 1 is there, when this equation have a number of cycle NF is 2 into 10 to the power 6. For these types of fat class, what is the D value and what is the M value? Here M value is 3, this M value is generally constant for all fat classes, but this D value is different for different types of fat classes. For 100 fat classes, the D value is 2000 into 10 to the power 12. Here 2 into, you can write 2 into 10 to the power 6 cycle equal to, you can say D equal to 2000 into 10 to the power 12 divided by, here they at that time this delta sigma r is the fat value to the power 3, NF equal to, you can say 2 into 10 to the power 6 cycle. Now, if this delta sigma r is, let us for these types of well configuration, let us consider if this del sigma r is let us 200 MPa. If it is del sigma r is 200 MPa, in this case what should be NF? This NF should be calculated like here, D will be, you should consider D will be this, and for this, because same configuration of well geometry we are using, and here just this del sigma r will be 200, here m will be 3, because that curve information you need to use, because you see this this types of well geometry is for a fat class of 100, what I am telling, understand. So, based on these things, for different stress strains for that types of joint geometry, what should be the fatigue life, you can easily calculate using this formula. And for this formula, what are the D value and M value is there, that is also given for different welded joint class. This you should keep it in mind. So, here one thing you can observe that generally this Eurocode shows the difference in stress range between neighboring curve is within a range of, you can see 15 to 20%. That means the neighboring curve, this 36, 40, 45, 50. So, this range is within a range of 15 to 20% difference. This you should keep it in mind. So, in according to Eurocode 3, 14 different types of you can say fat class are there. What are those 14 classes and what are their joint geometry, little bit I am just showing. Like I have already shown you for 36 category 36 fat class, that means its fatigue strength is 36 for a number of cycle of 2 into 10 to the power 6 cycle, that is 2 million cycle. So, if the well geometry is like this, that means lap types of joint, overlapping joint and double sided fillet types of joint is there, this is one fillet, this is another fillet, and it is subjected to a transverse load del sigma, that then what happens, what should be a fat value, that things is given generally here, what I am telling, understand. Similar types like what happens if the category 45, when we consider 45 category. So, 45 category generally age attachment is there. So, this is a specimen with this, there is a age as a attachment of the another specimen is there. So, here the welding is done, what I am telling, understand. This is 45 category. Then 50 category means end of the long flat plate, or you can say cover plate, one cover plate we use, here you see. So, if this types of configuration you will use for some structure, there directly you can consider what is the fat value. So, according to this fat value you can decide what is the D value and what is the M value. Now, this structure if it is subjected to a particular stress range, then what should be its life, you can easily predict from the equation which I have shown, that is NF is equal to D divided by del sigma to the power M. So, based on this fat value you can easily find out what should be the what is called fatigue life for any types of what is called stress range, if you know the fatigue standard. Category 80 or 71, this is generally I have shown here, it is generally most short attachment, you can see it a short attachment is there, or there can be a stud types of stud mean nut bolt types of things you can say. So, that is generally called stud bolt is attached to a plate. Okay. So, for these types of configuration generally fat value is considered either 80 or 71. This is generally a short attachment away from edge, and it should not be up to edge, it is little bit inside the edge. What is the 100 categories? Just I am showing. Generally this 100 category is you can say it can be transverse butt weld with both sided weld joint, you can say double sided weld joint, or it can be you can say longitudinal fillet weld. Longitudinal fillet weld in the sense here the load is acting along the longitudinal direction or along the parallel to the weld direction, that is why it is called longitudinal fillet weld. So, there generally you can get a FAD value which is within a range of 100, what I am telling, understand. So, here whatever the different types of joint geometry I am showing, that is the joint geometry based on different FAT classes, this you should keep it in mind. The FAT classes in the sense for different types of joint geometry, what is its fatigue strength value at a cycle of 2 into 10 to the power 6. Now, we will solve some problem, one what is called nominal stress approach. Why this is required? Because once we will solve some problem, then our concept will be further more clear. And so, in first problem I will show you how to extrapolate the data for finding out the number of cycle for a welded structure, that I am just going to show. So, in first lecture itself I have shown generally fatigue life you can calculate is equal to N into Nf equal to, you can say, or N is equal to Nf into FAT divided by sigma nominal stress to the power m. This equation is for a failure probability equal to 2.3%, this you should keep it in mind. If it is 2.3%, generally this probability factor is used here inside this equation phi. So, once this failure probability is 2.3, at that case generally this phi value become 1, this you should keep it in mind. This illustration I will just discuss here, that will be based on a failure probability of 2.3%, or you alternately you can say probability of survival is 97.7%. This you should get. These things all other way also you can say, that is generally 100 minus 2.3 is the survival probability, this you should keep it in mind. So, this Nf is what? 2 into 10 to the power 6 cycle according to FAT classes, that already we know, and m value generally considered as 3, which also I have shown. Now, here I am showing, so for calculating the number of cycle for a nominal stress value sigma nominal and for a particular types of joint geometry, these FAT values we can easily calculate, that we need to know. Nominal stress for a particular types of joint geometry, how it is calculated, that we need to know. So, I have already told you, if the joint geometry is simple, then what happens, we can calculate the nominal stress very easily by using some equation of mechanics, which I have already told you. Another method generally we use, that is called numerical method using finite element analysis, that things also I have shown. So, in finite element analysis, how to find out this nominal stress sigma nominal, that I am going to show. So, let us consider the following example. This is an example of the what it is called a specimen. So, here you can say two gasset plate, this is one gasset plate, this is another gasset plate, and what happens, it is welded around the plate. You see this plate welding is done around the plate, and it is subjected to a load like this sigma. Okay. If it is subjected to a load like this, then what should be its nominal stress value, that we need to find out. That means, what should be its nominal stress value, and if we can find out this nominal stress value, then we can easily find out what is the fatigue life for any types of loading case. It is subjected to a stress generally amplitude of 80 MPa. If it is subjected to a stress amplitude of 80 MPa, for this case what should be its nominal stress, okay, that generally we need to find out. So, for this generally what we need to do, it is observed that these types of class details generally on plate and at top side of the plate, on gasset plate at top side, generally these types of joint geometry detail generally available in what is called fat class. This in fat class where the structural detail generally grouped into different different name in a tabular form. Like this is the these types of joint geometry, this data we can get structural detail at a number 521. What I am telling, understand? So, in this 521 generally this is a longitudinal types of fillet weld. Why it is called longitudinal types of fillet weld? Because load is acting along the welding direction. That means, this is the weld, this is the weld direction and the load is parallel to the weld, that is why it is called longitudinal types of fillet weld. If the load is perpendicular to the weld direction, then that is generally called transverse fillet weld. This you should keep it in mind. So, for longitudinal fillet welded gasket of length L, generally what is the FAD value, that means FAD value means fatigue strength value for steel material and for aluminum material, that is given here. Here one thing you should keep it in mind, if the length of this weld, this length of the weld is less than 50 mm, then generally it has a FAD value is 80 MPa for steel and 28 for aluminum. Similarly, if it is less than 150, then it is 71 MPa and 25 MPa for aluminum. If it is less than 300, then you can say it is its value is 63 and you can say for steel and for aluminum it is 20. If it is greater than 300, then you need to consider this FAD value for steel is 50 and for aluminum it is 18, that you can see here from this table. Now, here generally this FAD value we can calculate based on this L value and this joint geometry. So, you see these types of double types of gasket geometry is not generally available in tabular form, but what I told you, if these types of exactly similar geometry is not available, then you should consider what is the closer types of geometry data is available for FAT class, that data we need to use for fatigue life calculation. So, you can say this table 1, whatever the data is provided, this geometry and this our whatever the example here showing, this geometry is closely related to each other, that you should keep it in mind. So, first of all, so we can consider here the FAD value is either 80 or 70 or what is called 63 or 50, that depends on what is the L value. This you should keep it in. Next slide actually I will show you, depending upon L value, another example there I will show you. Generally here I am showing how to find out this nominal stress, that procedure generally I am just showing here. So, for finding out the nominal stress of this geometry, generally here we need to do finite element analysis. This finite element analysis you can do by different FEM software. FEM software are there. What is FEM? FEM means finite element method. Finite element method. Okay. This finite element method is a numerical method. Numerical method generally is a approximate method. Another method is there, that is generally called analytical method, which gives us a accurate result, exact solution which gives. So, numerical method generally gives approximate solution, this you should keep it in mind. So, this FEM software generally we use for finding out the nominal stress. Like what are the FEM software we can use, that can be ANSYS software, Abacus software is there, then Nastran software is there, then COMSOL software is there. So, these are the different types of software by which we can do the structural analysis for finding out what is called nominal stress. So, stress distribution pattern we can find out. So, for this geometry you can observe that here this geometry either completely you can model it and you can find out the stress distribution from this toe to away from the toe zone, how it is varying, that you can see, that way you can find out, or you can find out as it is a symmetric types of geometry. So, here you can take symmetry means it is symmetry about this vertical axis as well as it is symmetric about horizontal axis also you can say. That is why here you can take what is called double symmetry of the geometry. Double symmetry of the geometry once you will take, then the geometry become like this. This is the quarter symmetry geometry, the quarter part of this weld joint. That means, let us consider this portion I am taking. So, let us consider this portion 1 I am taking. So, this portion 1 we need to model in this finite element software, and after that we need to use the symmetric boundary condition. Here on symmetric boundary condition, here another symmetric boundary condition will be there. So, this symmetric boundary condition we need to use, that is generally available in ANSYS software itself. Once you will practice it, there you can easily get the idea. Then after that we need to apply the load. Here the load amplitude is given at 80 ampere. If it is axial types of tensile types of axial load amplitude, for that case it is observed that once you plot the stress distribution from the toe of the weld, you can say from the edge of the weld to away from the weld, you can see from the away from the weld about this along the weld line direction. There you can observe that generally at the weld toe location, there the stress magnitude is very high. Because why there the stress magnitude will be high? Because you know, like here how it is little bit I am showing.